So today we're starting a new topic, and that is representations. This is a pretty important one, so pay attention. I mean, you should pay attention to all these videos, right? So how do we define representation? As always, we're going to let G be a Lie algebra. Man, they're loud. I'm going to let G be a Lie algebra over a ring we're going to call K. And it's going to have a module called M. And so a homomorphism of G into the general linear Lie algebra of M, which keep in mind is just the endomorphisms of M, is called a representation. Representation of G on M. It is called faithful if it's injective, which basically means it's just preserving all the structure of G. I'm sure you know what injectivity means. If K is in fact a field, and not just a ring, the dimension of M over K is going to be the dimension of the representation. Representation. And of course we have, that's like an example. We can define representation AD from a group G to the general linear group of G as a K module by sending each X to, well, adjoint of X. Remember, this is the adjoint representation. This is why it is a representation. Because it's a representation, yeah. Okay, so a representation of G on M is thus a K linear mapping. We're going to call it rho of G into, as I've said, the endomorphism module of M, such that rho of the Lie bracket acting on M is equal to rho X, rho Y acting on M minus rho Y, rho X acting on M. All right. I'm just trying to read through something here real quick. Alright. Let U be the enveloping algebra of G. Maybe I should be writing this as UG from before. So there is a one-to-one correspondence between representation of G on M and representations of its universal algebra on M. I'm going to switch between the two notations we've developed. Hopefully it doesn't get too confusing. And it says very confidently, we know there is an equivalence between representations of the associative algebra U and left U modules. And I guess what this is saying is that you can turn any U as a representation. If U is a representation on M, then you can define M as a left U module where the scalar product is just the representation acting on the elements, and vice versa, I believe. So I think that's pretty straightforward. Another definition here. We're going to always have G be a Lie algebra over K with enveloping UG. A unitary left module over U is called a left G module, or sometimes simply a G module. And I think we've seen G modules before, right? From before, where it's essentially a module which also is compatible with like the Lie bracket structure, potentially. Yeah. Okay. Now, we see If M is a G module, and X is in the universal algebra of G, developing, M will denote the homothety. Homothety? I don't actually know what that is. I'm gonna have to look that up. Of M defined by X. Now here's a quick question. What is a homothety? Homothety. Let's look it up. Well, it looks like I don't have internet. Anyways. Well, I'm gonna have to look this up and get back to you on that one. Oh, I think so. It says a homothety is essentially an affine scaling of space. I'm not 100% sure about this, but I think XM is essentially the image of either the image of M under X or the function on M defined by X, a la the adjoint representation. And one other question I have, what is a unitary module? Does that just mean it has a unit? See, this is why I put a disclaimer at the start, like, I am not an expert in this. A unitary module is a module of a ring's identity such that multiplication by the identity is the identity operator. Alright, that makes sense. So a unitary rate module over UG is called of course, a rate G module. And of course can be identified with a left U inverse module, where this circle is just the opposite group. Remember, the image of U under the anti-automorphism sending each element to its additive inverse, so it reverses multiplication. Oh, and they're going over that right here. Let phi be the principal anti-automorphism of U if M is a right G module then the left G module is defined on M by the way that A acts on M is the way A is acted on from M is acted on from the right by the opposite of A. And just quick reminder, this is for M in our module, A in our universal group. And keep in mind, we can freely switch between representations of a group and its universal algebra, enveloping algebra, same thing. Alright, and from this we see that we can translate module theory into representations. Because we can express every representation as a module, we can just switch it over. I think that's just a really big fly. Okay, so let's look at some of these translations. To representation, rho and rho prime of G on M and modules M and M prime are called similar or isomorphic. If their if the G modules M and M prime are isomorphic. This is equivalent to saying there exists an isomorphism U of the K module M to M prime such that rho prime of X, the representation of X on M prime, is equal to representation of X on M through a change of basis by U. Second condition. We're going to let rho I be a representation of G on a module Mi across various i's in an indexing set. Going to let M be the G module which is the direct sum of these MIs as G modules. And so there is then a representation rho of G on these M, on this M, which is called the direct sum of these rho i's, and is of course denoted similarly how I denoted the direct sum of the G modules. It is the sum of these rho I. If we have an element of M comprised of individual i's, and an element X in our algebra, then X acts on M through rho essentially component-wise, pairing up each of our individual rho i's with its corresponding Mi. Alright. Next topic here. Representation rho of G on M is called simple or irreducible. I guess I should write that out given it's a definition. If the associated G module is simple. That is, there are no submodules which are K modules of M other than the trivial ones of just 0 and the entire M. There are no submodules. Stable under all row X. Of course, 0 and the entire M are going to be always stable under these. A class of simple G modules. I gotta talk louder because there's stuff going on upstairs. Defines a class of simple representations of G. Alright. Well, there's more terms to carry over, a couple more at least. A representation row of G on M is called semi-simple or completely reducible. If the associated G module is semi-simple. That is, we can row is simple, is similar. It's isomorphic to a direct sum of simple representation where every submodule or that every submodule by K of M stable under all row X has a, I would call it a stable supplement. It just means stable and also stable under each row X. Alright, number 5. Let delta be a class of simple representations of G corresponding to a class C of simple G modules. We're also going to let rho be, why does it wait till I talk? Be a representation of G on M. Oh man, what? I'm gonna have to look this up after. The isotypical component MC of species C of the G module M is called the isotypical component of M of species delta. Sorry, one second. This component is the sum of the sub-K modules, the submodules by K of M stable under the rho of X and on which the rho of X induce a representation of class delta it is the direct sum of certain of these submodules if MC is of length n, then rho is said to contain delta n times the sum of different MC is direct being equal to M if and only if rho is semi-simple. So let rho and rho prime be representation of G. It does not say where they're acting on. Rho prime is a sub-representation of rho if the module of rho prime is a submodule of rho. So let M be a K module the zero representation of G on M defines on M a G module structure and this is called a trivial G module. Now they continue talking about species, but the thing is there's a lot of talk here continuing about species, and I don't really know what a species is. So I feel like I'm going to try to look that up here. Alright, so the rest of this chapter is on species, and I don't understand what that means, so we're going to skip it. And if that is a problem, I will try to rectify it in the future, but I don't have the... It's assuming you know species from a text, which I don't have, and I won't be able to find in time for this video, so that's just everything now. I don't see any mention of it later on, so hopefully we can do one more section here pretty easily. And that section is the tensor product of representations. So we're going to let G1 and G2 be Lie algebras over K with they both have a module which we're going to call Mi. I'm going to let UI be the enveloping algebra with the canonical mapping sigma I. Then we have that MI is a left UI module, as you saw before, and hence the k-tensor of M1 and M2 K is the tensor and not the second multiplicand. This has, just make sure this is a K. This has a canonical left U1 tensor K U2 module structure. Now, U1, the k-tensor of U2 is the enveloping algebra of G1 times G2 and the mapping of the pair x1 and x2 and G1, G2 being sent to sigma 1 x1 tensor 1 plus 1 tensor sigma 2 x2 is the canonical mapping. Is canonical. Hence, there exists a G1 times G2 module structure on this M equals M1 K tensor with M2 such that K1 and K2 in M acting on the tensor of M1 and M2. This is equal to sigma 1 of x1 tensor 1 plus 1 tensor sigma 2 of x2. This is going to be acting on M1 tensor M2. Keep in mind this is just sending G1 times G2 to its enveloping algebra. And this is, of course, going to act as x1 in M1, acting on the first module element, tensor M2 plus M1 tensor x2 in M2 acting on M2. This defines a representation of G1 times G2 on M. Now, if all three of these are the same, if G1 and G2 are the same, I guess, and we're going to call it G, I was going to talk about the homomorphism X into X with X, kind of a familiar map here, of G into G times G, composed with the above, defines the representation of G on M, and which is a G module structure on M, likewise, such that x to the M acting on M1 tensor M2 is equal to xm1 acting on M1 tensor M2 plus M1 tensor xm2 acting on M2. And analogously, we get a free proposition which states that we're going to have G be a Lie algebra and we're going to let Mi be a G module. Then on the tensor product in K of these Mi, of which there are n copies, there exists a unique G module structure such that the action of xm on the tensor of a series of Mi is equal to the sum of essentially a tensor volume with component xmi acting on Mi. And that's the end of the proposition. The corresponding representation is called the tensor product, of the given representations of G on MI. In particular, if M is a G module, the above proposition a G module structure on HMP being the P being, I believe this is unreadable, being the tensor product, I believe, of P copies of M. Yes, and hence on the tensor algebra of M, which I'm just gonna write TM because my hand is tired. And that formula shows the one that we just did, XM acting on the tensor, we see that for all x in G, xt is the unique, and I guess I should specify here this sub t, I believe is just showing from where the x is acting. It's the unique derivation of the algebra T extending x to the m. We see that xt defines by passing to the quotient a derivation of the symmetric algebra on M hence the symmetric algebra of M can be considered a quotient G module of T and these xs being derivations of Sm. I guess this should be xsm. One more remark before we'll call things here. If we consider G a G module by the adjoint representation, then we see then x of m defines by quotient a derivation of u of g which is just the inner derivation defined by the image of x in the universal algebra, then UG can be considered a quotient module quotient G module, that is, of T. If K is a field of char 0, then recall we have a canonical isomorphism. Is also a G module isomorphism. And we will call it there for now. I will try to look into that species isotypical component thing. I'll see if I can get that copy of Bourbaki, like the later chapters. If not, we might just like hope it doesn't show up again, because I don't, it seems more like a side note. I don't see it occurring directly skimming forward, but we'll see.